There's a Wikipedia page which says that if you see this number coming up, 691, that's a marker. That means there must be Bernoulli numbers going on, and if you see this denominator in the Bernoulli number, you got to start thinking there's modular forms in the background, because this is the Bernoulli number, B12. So this wasn't noticed using rational arithmetic. We had a long decimal expansion of something. And actually, when I first did this, I forgot to subtract on pi, and so I had some number, and I decided just to look at this website. It's called the inverse symbolic calculator. You type in a number, and it says, your number is this crazy expression. And it said your numbers occur in the digits of pi. So everyone's phone number occurs in the digits of pi. So I just thought it was useless, and I clicked it. But just as it was closing, I noticed on the corner of my eye it said starting with the second digit. Okay, so that's worth the second one. So I realized that the number I had was 1.0415926654. I didn't recognize it in that form. And once I subtracted the pi, oh yeah, 21 times. Okay, good. 2.1. So we have a whole bunch of these, a whole bunch of rationalities. Some of them were derived using derived and not rigorously proved. But most of them were just experimentally found. And we had basically we could control. We knew that there were these functions to order 2 at all roots for the Leech lattice and for E8. And in fact, for the Leech lattice, we knew it at square root of 2, even though that's not a lattice vector. So that's a huge amount of information. So now I've got 5 minutes. Now let me point out where Marina comes in very nicely. So
you have 15 minutes.
15 minutes?
Till noon. We started at 11.
Until noon.
We started at 11:10.
Okay. Oh gosh, what do I think this thing to say? Okay. All right. Let me make another interesting remark at this point. The actual details of the Leech lattice and the E8 lattice are completely irrelevant at this point. In fact, I don't want to speak for other people, but I certainly can't, off the top of my head, give you a definition of the Leech lattice correctly. I mean, I can give you an abstract definition, but it's not something you carry around in your wallet, printed out as 24 vectors and 24 components. I mean, but the only thing that matters are these basic properties, that it's even unimodular lattice. At this point, it's become harmonic analysis completely. It's a function of calculus in one variable. This Fourier transform is not the usual Fourier transform in one variable. It's really a radial Fourier transform. So you think of this as a radial function saying 24 variables, and then apply the 24-dimensional Fourier transform to that. So here's my interpretation. This is not how Marina first thought of it, but this is a very good way, I think, to think of line construction. So let me, I'll call it a lemma, but maybe we should call it theorem. And I'm not stating the analytic conditions just because they're not actually necessary for the proof. I guess I'll introduce this to Marina. Let's assume F is holomorphic on the upper half plane. And let's let epsilon be a sign, plus or minus 1. So this is just to control the sign of the Fourier transform. Okay, so let's assume 2 conditions. Just to clean things up, let's just make sure E is divisible by 4. Otherwise, there's some issues with square roots. So the first condition looks a little like modularity. Second condition does not quite look like modularity. It's got a lot of functions on the left. So this is amazing. So this is giving us a way to construct radial eigenfunctions. Now, there are many ways to construct radial eigenfunctions. But what's phenomenal about this formula is it has the sine pi r squared over 2 factor. Yeah, and I think I wrote it incorrectly. It should be square. This is really a very clever idea. The sine squared is factored on the outside. It's daring. Now, of course, you might want to factor sine squared out because most of these roots are double roots. And sine pi r squared over 2 has a double root anytime r is a square root of an even integer. That's perfect, except it doesn't always have double roots. It doesn't vanish at the origin. It doesn't even vanish to order 2 at r1. In fact, the Leech lattice case, there's square root of 2 where it's not going to vanish either. So there are places where this integral is going to not be nice. It's going to have to be defined somehow through some analytic continuation and they have poles. But this framework is amazing because it separates something out, allows for poles, and then you have to determine in here where the problems will be. So she got this to work for dimension 8, and then we got it to work for dimension 24. This is the key sort of background to it. And this is something that, of course, Henry and I were very aware that modular forms are related to eigenfunctions because, I showed you before theta, but there's a different class of modular forms. In order for this thing, let's just look at the first point where there's have to be some issue with a single root. This integral will have to blow up when r is r1 if it's going to work. Because otherwise it would be a double root at r1. There should only be a single root. So there's going to have to be a pole there. For a pole to happen, and say this was a modular form in the Q expansion, you'd have to have something blowing up there. Because this will be decaying. So if you plug r to be square root of 2 here, then this part of the integrand is decaying like e to the minus 2 pi times the imaginary part of z. So this is going to have to grow up, to blow up. So this will be blowing up. So we're in a situation here where we need these identities to work, and we're going to have, or if things are going to work out, we're going to need have to blow up at the cusps, wherever they may be, at least at some cusps. Now, the reason I said the analytic details aren't important is that this is telling you how to construct the function. Once you have it, then it's easy to write a proof of everything very rigorously. It's not so important here what the class of functions is. So, to work out the eigenfunctions are, we need to get these to work. And this epsilon here, in the first case, it's not so hard to get this to match up. But when epsilon is -1, it's really tricky for the second equation. Sorry, when epsilon is +1, it's tricky for the second equation. So let me now show you the answers. The answers are at the back of the book. I think I'm just going to focus on the Okay, so I need to tell you how to get the even eigenfunction and odd eigenfunction. So let's do the even one first. So for the even one, we take f of z to be z to the d over 2 minus 2 times phi of minus 1 over z. Now, if you plug that in here, that's convenient because then you just basically need something like periodicity. So if phi is periodic, phi satisfies phi of z plus 1 is phi of z, then this first condition is met. And if when you switch z to z plus 1, if it transforms by a sign, then it would work even with epsilon equals minus 1. So this matches the first condition. But to do the second condition, when you transform it in this language, you get a different type of identity. And that puts you exactly in the realm of something called quasi-modular forms. So this is a topic that was studied a lot by Zagier. And so I first came across that about a year ago because some string theorists kept asking me questions about it. And I didn't know the theory at all. Thankfully I learned it because it was very clear. So a quasi-modular form is an expression like this. So it's e2 to the j times hj. So I'll write j as a finite sum. And so hj is a modular form of weight k minus 2j. Gamma. I mean, you can include poles at infinity, which I'm not saying so much about, but those who are aware of that decorates on. So basically, E2 is not modular, as you just learned this morning. But if you take, E2 is almost modular. Zagier calls it quasi-modular because it has some interesting transformation law, and then that transformation law yields formulas like this. So I can write down those functions for you. So this is the theory of Zagier, and Miazovska was Zagier's student. So for E8, up to scaling, phi is given by the following formula. So this is not how it was originally written, but I think it's useful to do it this way. So it's some combination of E2, E4, and E6 divided by delta. So delta is Ramanujan's test form. Delta, in case you want to see the formula, it's E4 cubed minus E6 squared, and it's normalized by 1728. And then for the Leech lattice, well, I don't know if you really want to see it, but here it is. So as advertised, it's a polynomial in the E2s whose coefficients are modular forms.
I'm sorry, it's hard to read that in the back. It's hard to read that in the back. What is that? Or just a messy expression?
Yeah, it's just some messy expression. Yeah, it's a messy expression where this is a modular form of weight 16. This is a modular form of weight 14 times E2. So it's sort of like it's called quasi-modular of weight 16, and then this one here is weight 12 times E2 squared. So this is an expression which is we found, and how do we find it for Leech lattice? I can't really speak for Marina how she found it for E8, but for the Leech lattice, we knew all these rationalities such as these, and we were able to match. We had enough of them. We were able to match them all up and find the right function. So maybe I can conclude with the odd eigenfunctions. You know, rather than just write formulas down, the formula is actually simpler there. But rather than write them down, maybe I'll be slightly educational. I'll mention the context there. The odd eigenfunctions come from gamma of 2. Gamma of 2 of weight 10, this is for E8. And then 14 for the each. I mean, it's really this divided by powers of delta. So the weights are actually negative in the end. But this is one way to think of it. And let me just maybe mention say it's highly useful. So if we want to study these, the space of modular forms of weight k for gamma of 2, let's say here, you can be more precise when it's half integral. Like let's say k is even. This space is, well, let me just degrade it. K and 2z. It's generated by the classical theta function, the Jacobi, and then it translates by st. Actually, this is all you need. You translate by st squared. It's just basically a sum of the other two. That's how you set it up. So it's a ring. It's really a polynomial ring of two generators. The symmetry is nice to do. There's 3, and you can calculate things very easily for gamma of 2. It's almost just as good as it is for SL2Z when you go to gamma of 2. So I thought I would just mention that's a useful trick. So these well, I put it on the 4th powers. So at that point, you know that the space is finite. You can again match up with numerical properties. All right, I think that now I'm definitely on that.
Any questions?
So, just to make sure I'm understanding what you're you're saying that in order, the even eigenfunctions come from those little f's, but they're all in the form of these big F's, right?
Yeah, so maybe it was a mistake to call this f here, because this is not the f that goes in the Poisson sum.
Yeah.
Yes. I should have called it something else. There's a change in notation. Yeah, so this was the f that goes in a Poisson sum.
Earlier in the lecture, you talked about how you need to be divisible by 8, so 8 and 24 would work. Will that always work for 16 or 32 or any other?
It seems that this doesn't give the right bound. I mean, in any dimension, this technique will give a bound. It may be hard to prove what the best possible bound is, but it's clearer than other dimensions. Well, I don't know if we looked at 16, but it's pretty clear that it doesn't come close to the right answers for other dimensions. Except 2. So 2 is known, and maybe there will be a modular form proof in 2 dimensions. But we don't have it.
Other questions? All right, there should be some lunch outside.